So welcome to Coding Interview Crash Course, workshop 4, I think. This one's about stacks and queues, two super useful data structures that have uses on their own, but also are super applicable across a whole variety of problems. So we'll be starting off on this topic today, but there'll also be a recurring theme in the next couple of workshops as well. So today's attendance code is Tower of Hanoi. Is it because it's a stack, Phil? What's the reasoning behind this one?
Yeah, it's like you have stacks of disks.
Yep.
It's a pretty popular problem that involves stacks, I think.
Alrighty. So Tower of Hanoi, get that in, get attendance points. Here's the link to today's slides. As we've got both the CICC, so Coding Interview Crash Course, and we spelled lesson correctly, so growth mindset. All right. This is a ACM-wide feedback form, I believe. Bill, do you have more to say about this feedback form?
Yeah, so let's get the link in the chat first because everyone
Good
wants to
point.
access the slides. And yeah, so the feedback form there is less of a feedback for the lesson and like the actual content, and more of a feedback for like how the pace of the workshop is and like this quality of the slides and graphics and like concerning accessibility. Since we're like pushing some new initiatives to like define accessibility measures and make sure that our slides are useful and accessible to everyone. So this is kind of like, I'm sure you guys seen this before if you guys went to like intro to CP yesterday or like advanced track on Tuesday maybe, or maybe not advanced track because that was before we made this. But probably seen this before. So this is kind of for us to evaluate how we should iterate on making our slides and our presentations more accessible.
Alrighty, so please do fill it out when you get a moment. It helps us all out. Okay, so let's jump into stacks. So stacks are just containers of objects that are inserted and removed as per the last in, first out principle. So a useful abstraction is a stack of books. So if you have a stack of books, you put a book on the top of the stack, and when you wanted to remove a book, you remove from the top, as opposed to like Jenga, I guess, where you can just like remove from anywhere. So it's like a stack of books versus a stack of whatever. But anyway, so I think the super important thing is just to remember the principle, which is last in, first out. Other operations you can do on a stack are like adding elements to the top, also called pushing. You can access the element off the top with the top function. You can pop an element off and get rid of it. And you can check if the stack is empty. If you're not able to access the slides, try signing in with your UCLA ID on your browser. I think it's restricted to the UCLA organization. Thank you. Okay, so in C++, the standard template library has a stack that's super useful. It avoids the pain of having to implement your own. So you have to include it with include stack. You declare a stack of objects with just a stack, the type. So this would be a stack of integers, call it whatever you want. You push elements to the top with the push function. You view the top element with top. You remove elements from the stack with pop, and you can check if it's empty using the empty function. And something that's super important to remember is that pop is void. So it just gets rid of the element on top. So if you want to access the element on top, make sure that you use the top function before you pop it off with pop. So always top before you pop if you want to see what's going on in your stack.
I'd just like to add something. This
Sure,
isn't
go
how
ahead.
this isn't like how it's like for other languages. Like I know for
Yes.
Python, if you do pop, it actually returns the element that gets removed, which is, in my opinion, I find pretty useful.
Yeah, I think there's, I was reading about this, and there's this whole like stack. There's this guy who's there's this whole like basically flame war about whether pop should return something or not. So I think the C++ guys went for separation of concerns or whatever. But yeah, so if you're using C++, remember to top before you pop, but always check your local language listings to see what will work best. So here's a visualization of stack operations. You push to the top, you pop off the top, and the top function returns what's on top of the stack. So apologies for the corny image, but if you push corn to the top, you pop corn off the top. Okay, similarly for queues, so queues are containers of objects that are removed and inserted as per a first in, first out principle. So useful abstraction is a line at a restaurant. And I should add that a line at a competent restaurant, because you want to make sure that the people who get in first are serviced first. So you add elements to the back, you access the front, you can also access the back, and you pop elements off the front, and you can also check if the queue is empty. C++ queue operations, make sure you include it using queue. Again, you can declare a queue of objects to be of any type that you want. You push elements to the end of the queue, view the front element. This should be front, my apologies, my queue.front. You remove the front element using pop, and you check if the queue is empty. Again, be careful while popping and check your local, if you're using a different language, make sure you check if pop is void or not. Okay, so here's something I found on Reddit. But if you're taking an Uber pool, you'd want your Uber pool to be a queue and not a stack. So here, if you're Martina or whatever, you picked up Martina, you picked up Kate, but then you dropped off Kate before you dropped off Martina. So this is what a stack would look like. So you push Martina onto the stack, you push Kate onto the stack, and then you pop Kate off, and then you pop Martina off. But ideally, I guess it would be a queue. So the first person in would be the first person serviced. Okay, so for the warm-up problem, I guess I'll hand it over to Bill. Bill, do you want to share your screen? I'll stop sharing.
Yeah, for sure. Also, one bit of trivia about the standard library for stack and queue. So both of these standard libraries are actually implemented off of another standard library data structure. I think it's called DQ, which stands for like double-ended queue. And basically like that's like a queue that can also function as a stack. Like you can pop and push from both ends. And so they're both implemented with like the same data structure. It's a fun bit of trivia if you're interested in using like a DQ when like you can't decide between whether you want to use a stack or a queue.
So I have a question.
But okay, so first I will, what's up? Go ahead, Alvin.
What's the runtime for like stacks and queue operations? Sorry to interrupt.
That's another good question. I think most of them are constant time. So pushing to the front, popping off, they're all constant time operations. I think empty is also constant time because it just has like a field, I'm assuming. And yeah. Okay,
right,
so
good.
I guess I will stop sharing.
Yes. All right, I can't see the chat, so I'm gonna assume everyone can see the screen.
Yeah, we can see it. Sorry.
Okay, cool. Nice. All right, so I guess I will actually head back to the problem statement for now, just so that everyone can get a good read. So basically, the idea of the problem is like you're given a string consisting of only of like these 6 characters, open and close parentheses for 3 types of parentheses, and you want to return true if the string is valid, and false if it is not. And I believe it is valid if like the parentheses make sense, like the parentheses of the open version of that parentheses will always have a matching closed version of that parentheses paired with it. And also, if you like continuously remove open and close parentheses that are adjacent to each other, you'll eventually result in like an empty string. So does everyone like kind of get the problem?
Yeah.
All right, cool.
Sorry, I keep forgetting we have to say something.
Yeah, I'm wondering if I can actually open the chat on my other screen. Okay, I can open the chat. That's good. Okay, cool. And so here we have like the 3 examples that were shown in the previous slide. So something like our first example here, like here we will return true because all of the open and closed parentheses are in the right ordering. Here we return false because this green open parentheses does not have like a matching green closed parentheses that is in its scope of like the black parentheses. So this doesn't make sense. And then here we have parentheses that have a matching closed parentheses within its own scope. So this does make sense. So we would return true in the first and last examples and return false in the second example. So does anyone have any like ideas or questions about the input, output, bounds, suggestions?
I have an idea that I think may work. I don't like really know how to like say it would work in all situations for sure, but I kind of have like a general method using stacks. So I would like consider looping through the string, and every time you encounter like an opening bracket, parenthesis, or whatever, you push it onto the stack. And when you encounter the closing counterpart, you check to see if the top of the stack is its counterpart. And if it is, you can pop it off and go on with your life. But if it isn't, you just return false. And then at the end, you should make sure your stack is empty so that for each starting parentheses, there was an ending parentheses.
Okay, yeah, I mean, I think that makes sense. Does anyone else have like dispute that that will work or have any other ideas? All right, cool. Looks like no one has anything to say. Let's say that, oh, is there a cool way to do it? I don't believe there is a cool way to do this problem. This is a pretty bog standard question. Stack.
If there is only one type of bracket, like there's only like parentheses and closing parentheses, there's another way to do it. I'll just let you guys think about that one.
Yep. Yeah, that is true. But because we have like so many different types of parentheses, this is kind of the way you have to do it. It's just sad. Okay, I actually have another question. I didn't see who suggested the solution that I was talking to, but let's say n is the length of the string, what would be the time complexity of your algorithm that you just suggested?
What's the time complexity of the one he said? I think it's
Right.
O of n, because every push or pop, it's just order 1, and you still have to go through the whole string or whatever.
Yep. So you only will process each character, each open parentheses at most twice, and close parentheses at most once. So it's bounded by O of n, even in the worst case. All right, great. So you mentioned that we should create a stack. So let's create a stack. So the standard library. Okay, and I guess like, does anyone have an idea of what to do next after we've created our stack? What should be my next step?
You
Right,
start
it's a
looping
loop.
through the stuff. Yeah.
Yep, sorry, I cut you off there. What were you gonna say?
No, I just say what I put in the chat. Just start looping through the characters in the string.
Okay, cool. Let's start looping through the characters in the string. And is there something we should do inside the loop?
You should check for, well, you should iterate through your actual string, but every character check and make sure that it's, if it, as you go through, if it's an open, push it to the stack.
Okay, so we want to basically
One
check
if case.
whether, right. So Daniel's right. We want to check whether or not the character that we're currently processing is a, so we're currently looking at SI, which is the character we're currently processing, but we want to check if this is an open paren or a closed paren. And so what could we do to check if it's an open paren or a closed paren? So I guess the obvious, oh, go ahead, Daniel.
Well, I was going to say, I don't know if you want to do this or this is dumb to do, but you could make a map and put all 3 of the characters that you're looking for in the map, and then just every time just check and see if it's in the map, or a set. You don't need a map, but you could check the set, see if it's in the set.
Right, exactly. So we can actually, to make our lives easier, just create a set of all of the open parens that we're looking at. So I believe we could do this by doing this. It's kind of messy because of all the parens, but okay. We can simply create a set where we store all of the open parens that we're looking for. And we can check if they match, the character C here matches a character in the set. So if we find it, and it's not equal to the end iterator, remember, this is how we search for something in a set in C++. Then what do we do here? If we do have a open paren that we're trying to process.
I think someone said just to push it onto the stack if it's an open paren.
So push this directly onto the stack. If it's open paren. All right, cool.
And then if it's not, compare to the top. So like your else case or whatever.
Right, right. And so let's say, okay, so Ryan has a good question. What's the advantage of doing a set like this versus a normal switch statement? So I think mostly it's up to your preferences. And I'm sure that the compiler will handle it similarly. I guess it depends on whether or not, like, if you have a lot of different switch statements. Like, I guess the idea is we have a dictionary of characters that we want to match, and if we want to do character matching and they all fit, like the idea of a single character, the symbol is a single character, then like it's just much easier to use a set when you're like writing it out for an interview compared to doing like a long switch statement. But of course, like when it's more complex, then it might be more beneficial to use a switch statement. But in this particular case, I think it's mostly going to be based on what you prefer to do and what makes more sense in terms of, does this fit using a set better or does this fit using a switch statement better? Yeah, exactly. I think Daniel's right. Basically, it's going to be the same performance-wise and like actual algorithmically wise, but this is just like much shorter to write. Yep. Okay, so Daniel mentioned that we wanted to now compare. So if that we don't find a open paren, because our input string is guaranteed to only contain either open parentheses of this type or close parentheses of this type, it means that like in this else statement, we know that the character C must be a close parentheses. Now, if the character C is a close parentheses, what can we conclude with another piece of information?
I'm sorry, do you mind rephrasing that question?
Okay, right. So if we know that character C is close parentheses, what can we conclude about the current status of the string? Like, what do we already know about the string? I guess we're missing one piece of information here. So let's say we know whether or not our stack has an element in it or if it doesn't. What happens when our stack is empty?
Oh yeah, we need an edge case for that.
Right, so we can't compare anything with the top of our stack if our stack is empty. Right, and so Nicholas comes up with a great idea that actually, instead of looking at an edge case, if the stack is empty, we already know that we don't have a valid string because it means that there is a close parentheses with an unmatched open parentheses, or like it doesn't have a matching open parentheses that we've already processed, which means that the string has to be invalid. And so if we know that in this case, that the stack is empty, we can just return false the entire program because we know the string that's been inputted is invalid. All right. And now we can go along with the rest of Daniel's method and check C, compare C with, so now what we want to do is we want to compare C with the top of the stack, right? And so like, what should I check here? Right, so we're asking right now if the top matches with the character C. But in terms of matching, we're talking about matching an open parentheses with its closed paren, right? So those are actually like different characters. So right, so like Yvonne mentioned, we're trying to find the complement. So what's like a good way of determining whether or not the top is the complement? So Daniel comes up with another great idea. Have a map that maps closed elements to their open ones. So we can create another map.
Does C++ have a way to access like the keys of a map as a set?
The keys of the map as a set. So are you asking if we can create the keys of a map as a set?
Basically, I'm just looking to cut down on the code we have, so we could just get rid of the unordered set in its entirety and just use the set of keys which we're mapping anyway. But if C++ doesn't have that functionality, then we definitely have to keep what we have.
Well, the nuanced
Okay,
difference is the map needs to, your key needs to be the closed value. So you're actually, like your key would be the inverse, if that makes sense.
Oh, Daniel, what are you suggesting we're mapping? Are we mapping the close to the opening or the other way around?
Yeah, the closing to the opening.
Oh, okay. Well, I mean, I guess either way you look at it, I guess in that case, could you look at the values of a map as a set then? Yeah, either way you look at it. I'm just looking to cut down on.
Yeah. I think you would need to use an iterator, and I think that would slow down your code.
Okay.
Actually, I do think, so I think I get, so who was the one who asked that question? Sorry, I can't see your name because I'm sharing my screen.
I'm Jonathan.
Okay, Jonathan, yes. So
Yeah.
I think that is possible. So like we can do something like this. Like, are you suggesting we do something like this? Use a map here, and we, oops. We map this to like this. And what we can do is, oh, good.
Oh, actually, I see what you could do, because you could compare to the top to use that as the key, and then compare that value to the element of the string. So yeah, you could do it with one.
Right. Because because we're guaranteed that the top of the stack is only going to be a valid open paren, right? So we can simply compare the mapped value of that top key with our character C, right? And here, just to answer Jonathan's question, so when we try to find a key C in open paren, we'll actually receive an iterator to the value at key C, or like, I guess, the container at key C. And so when we make this comparison, we're basically saying this is not equal to the end iterator, which is returned whenever you can't find a container for that key. So this works for both maps and sets in C++. So we don't actually have to change anything here at all.
All right, cool. Thank you so much.
And so here we can simply compare if I think this is how you do it. If the value so if the value of the key that we check at the top matches the character C, then what should we do here? So in this case, we've found that the top of our stack is the complement of the parentheses that we are currently processing, which is the closed parentheses. So now that we found that, is there anything we should do before we move on? Right, so we should actually pop the top of the stack. And is there anything else we need to do?
Should we check if the stack is empty at the very end, or am I going too fast?
That is something that we should do at the very end, but before we move on, there's another condition that we need to check, right? So this, we pop the top of the stack when we find the complement of the top of the stack matches the character that we're currently processing. But what happens when it doesn't match? So what happens in this final else statement? Right, we can just directly return false here, because we know that if it doesn't match, it means that there's no matching parentheses, so it's not a valid set of parentheses. And finally here, I think, was that Daniel who the other Daniel who just mentioned that we should check whether or not it's, the stack is empty? Sorry, I couldn't see.
I didn't see who said it either, but it wasn't me. They are correct, though.
Okay. Yes, they are correct. So now we know that, so what is the condition here of the size of the stack? When do we have a valid string and when do we not have a valid string based on the size of our resulting stack?
I mean, if the size is greater than 0, then it's invalid.
Mm-hmm. So yeah, so if the size is greater than 0, then it's invalid. And if it is 0, then it's valid. So we can directly like return that statement. So if it's 0, then we'll return true. Otherwise, we can return false. And we've then solved the valid parentheses problem. Yeah, you guys have solved your first stack/queue problem. Super exciting. Yay.
I like that return Boolean check thing you did there at the end. That's nice. I always forget you can do stuff like that.
Very concise.
Yep. For sure. Yeah, no, actually, I really liked, I think Jonathan was the one who mentioned this, but using a map here, a single map to do both checking for open parentheses and for checking for the complement. This was like super cool optimization. Very cool, very cool.
I do have a quick question to ask about how I guess C++ handles the dot find. So if we're being asked about like
sure.
time complexity, since it is an iterator, rather than so I'm used to I'm more of a Java sort of person. So in doing the same operation, I would be actually looking at the set of keys and just seeing if the hash exists, and that entire operation would be O of 1. In this case, is it sort of like O of the number of sort of keys that we have in that sort of mini step that we're looking at?
No, so for unordered maps, in the standard library, it's also implemented as a hash table.
Okay, gotcha.
So when we're looking at find, we're looking at a hash function as well. So the dot find operation for both unordered maps and unordered sets are both O of 1.
Okay, sure. Okay, thank you.
Yep. And like, yeah, an iterator is basically like, yeah, kind of like a pointer to the container for that specific standard library data structure. All right, cool. Does anyone else have any other questions? All right, Ivana has a great question. Should we generally use the unordered set and unordered map for hash maps and hash sets? So I think, I don't know if we went over this, but basically in the C++ standard library, there are unordered maps and regular maps and unordered sets and regular sets. And the core ideas behind unordered maps and sets and ordered maps and sets are different. Underneath the kind of like containerization, the ordered maps and sets are implemented using binary search trees or just other types of like search trees in general, because we need to like maintain an ordering for them. Whereas the unordered maps and sets are implemented using hash tables and hash sets. So at its core, those two are different data structures. And Daniel had a great point there. The ordered ones are usually take like O of n log n or like O of log n to do finds. Whereas the unordered sets and maps will only take O of 1 because they're two like concise different data structures and they serve different purposes. If you're like, to answer Ivan's specific question, if you're looking for a hash map and a hash set, you should be looking at the unordered map and the unordered set. All right. I think before we head off to break, we can do a short poll of like how you felt about this problem. I think right after this, we are going to head off to a break, I think.